In this video, we will be doing a review of the AP Physics 2 Fluids unit. This unit we covered many different topics. First one we covered was density. Then we covered pressure, Pascal's principle, buoyancy, and fluid dynamics. First topic we covered was density. We didn't really cover this at a very great detail. We just know that rho is the variable we use for density, and it's equal to mass divided by volume. We measure it in kilogram meter cubed in this course. We also learned about something called specific gravity, which is the relative density of a material with respect to water, rho over rho of water. The density of water is 1 gram per centimeter cubed, which is 1 kilogram, or I'm sorry, not 1 kilogram, 1,000 kilograms per meter cubed. Pressure is defined as being the force applied to an object divided by the area over which that force is applied. It can be measured in Newton per meter squared, or more often we're going to measure it in pascals. One thing to note, if the pressure on two sides of a barrier are different, there will be a net force. So if I have a barrier and there's pressure 1 and pressure 2, if pressure 1 is greater than pressure 2, the area of this barrier is constant. And pressure equals force over area. P1 equals F1 over that area. P2 is smaller, would have to be equal to a smaller force over that same area. So we have a net force coming from pressure 1. F1 would be greater than F2. Also, when we talked about pressure, we learned that pressure in a fluid is dependent on your depth in that fluid. This is called the gauge pressure. Pressure equals the density of your fluid times G times the depth. This is essentially a measurement of how much of the fluid is sitting on top of your point of reference. We also learned that the total pressure inside of a fluid would be equal to the pressure of the atmosphere plus this gauge pressure. This brings us to Pascal's principle. Pascal's principle is a statement that in a continuous fluid, assuming that the depth is not different, the pressure is constant. So by that we mean F1 over A1 equals F2 over A2. This is typically applied in the context of hydraulics, where we have a fluid in a small surface area that is connected up to a fluid with a large surface area. I can apply my F1 here, and I get my F2 there. And I drew those vectors wrong. That vector should be much bigger. So I can have a small force on a small area giving me a big force on a big area. There is also a continuity that we have to consider. If I move this piston by some value delta x1, this piston will be moved by some value delta x2. This is because when I move my first piston, I'm displacing a certain volume. The volume is area times that delta x. So area 1 times delta x1 equals area 2 times delta x2. If I have a small area 1 and a big area 2, I will have a big delta x1 and a small delta x2. So our example would be hydraulic brakes. And I think my pen may have just run out of ink, so I'm going to pause right here. And I'm back. So brakes. In hydraulic brakes, you're going to be applying a small force to a small area, or your foot pressing against the your foot pressing against the brake pedal, and that is connected up through your brake line to a large area, giving us a large force. So the drawing above is essentially what's happening in your brakes. Next topic we covered was buoyancy. The buoyant force is exerted on an object by the fluid that the object has displaced. So FB equals the density of the fluid times the volume times gravity. Typically the fluid is going to be water, although we could think of the buoyant force acting on, let's say, a helium balloon. The fluid that's displaced there is the regular air. If the volume, this is the volume submerged in the fluid. The volume submerged is equal to the volume of the object if it's completely submerged. If it's not completely submerged, the volume submerged will actually be less than the volume of the object. If the buoyant force is less than the force of gravity, the object will sink. If the buoyant force is equal to the force of gravity, it floats. If the buoyant force is greater than the force of gravity, it will rise. Many times when we say float, we refer to it floating on the surface. If it's floating on the surface, then that's because it's reached an equilibrium where the volume submerged and the volume of the object are different. One thing to note, the force of gravity is equal to mg, but we can find the mass by using the rho, density of the object, times the volume of the object, times gravity. And a lot of times buoyancy questions will ask us to use that. The last thing we hit on was fluid dynamics. For fluid dynamics, we have to remember the two big conservation laws, the law of conservation of matter and the law of conservation of energy. That will dictate our equations. The first equation we have is called the continuity equation. This is a corollary of the law of conservation of matter. This is a simple statement that the volume that flows into a specific area per unit of time has to be equal to the volume that flows out of that area over time. And if volume is equal to area of the pipe times the length, a certain length of pipe, then we can get area times that length over time equals the new area times a new length over time. And delta x over t is velocity. So area 1 times velocity 1 equals area 2 times velocity 2. So to kind of illustrate this, here I have a certain volume in this pipe, which could be calculated by delta x1 and could also be calculated by the area, surface area. And here is another length of pipe, which has delta x2, but it has a smaller area. But when I multiply those two together, delta x1 and area 1 versus delta x2 and area 2, I should get the same value for velocity. So this right here is our continuity equation, just saying that the water or the fluid that flows in has to equal the fluid that flows out. Typically, this means that as we can constrict the pipe, our velocity will increase. Then we had Bernoulli's equation. And we really need to remember that this is a corollary of the law of conservation of energy. Because a lot of times when we misuse Bernoulli's equation, it's because we forget that we're talking about energy. The equation is that the pressure at one point is equal to rho GH at that point. This rho GH is a measurement of the potential energy of the fluid at that point, plus 1/2, hold on one sec, back, plus 1/2 rho V1 squared. That's a measurement of the kinetic energy of the fluid at that point. P2, this is the pressure at another point in the pipe, plus rho GH2, plus 1/2 rho V squared 2. So, just a quick note, rho GH is not the same as rho GD, even though sometimes it looks like they're very similar. This, in Bernoulli's equation measures the potential energy of the fluid. And this right here is our gauge pressure equation, which we use to describe the pressure at a fluid when we are submerged, but that is only ever for a static fluid. If we're talking a moving fluid or a dynamic fluid, we can't really talk about gauge pressure. So those were the big topics that we had in our fluid dynamics unit for AP Physics 2. Hopefully this review will help you refresh your memory and get you ready for the practice problems.